This is section 6.2, the normal model. Let's take another look at the sample distribution of heights of the sample of mothers from the Galton's mother and daughter data set as used in Applied Linear Regression 3rd edition. The histogram is shown below. Comment on the shape, center, and spread of this distribution. So taking a look at our histogram, we could say that our shape is unimodal, symmetric, the center looks to be about 62.5. So this looks like the center around here. We could say is 62.5. And the spread, we could comment either on maybe on the range, or we could kind of get an estimate for the standard deviation. It looks like the data goes out to 71. So we could say, well, 71 minus 62.5, that's going to, all of the data is going to be about within 3 standard deviations of our mean based on the empirical rule. So our standard deviation's probably around 2.83. And that's just a rough estimate based on the empirical rule. So what is the best model for this type of distribution? So this histogram that we're seeing, we see a lot of data has the same shape. And so having a mathematical model is very useful. And what's been found is that a model called the normal model fits this type of data. So the normal model, we can see it's on the red line here, looks like this, a little wiggly. It's symmetric and unimodal, and it fits this type of data quite well. And it's really useful for us to talk about the probability of observing things given a mathematical model. So let's look at some of the features of a normal model. So it's the most widely used probability model for continuous variables. So it's extremely important. We're going to be using it for much of the rest of the course. Let's take a closer look at our features of the normal model before we consider how to use it. So a normal model is unimodal. We saw that. And symmetric. And it has the famous bell shape. Okay, so the bell-shaped curve that comes from the normal model. The mean and standard deviations are the two characteristics needed to distinguish one normal model from another. So those are the two pieces of information you need to know in order to know what the normal model that you're considering will look like. The mean is the balancing point. It's the mode, it's the top peak, okay? Because the normal model is symmetric, the mean is the exact center of the probability distribution. The standard deviation measures the spread of the probability distribution by telling how far away typically the values are from the mean. The normal model uses this notation, which we want to become familiar with. So the N is saying it's normal, and then it has the two pieces of information you need to know. First, people put in the mean, and then comma, and the standard deviation. And this is like conventional. This is the way you'll always see the normal model written. The normal model can be called the normal curve, normal distribution, or the Gaussian distribution. The normal model represents the distribution of probabilities for many real-life continuous numerical variables. Each probability is represented by an area underneath the curve. So we're going to look at how we can figure out probabilities on the next page. So the following contains 3 normal distributions that serve as models for the distribution of exam scores from 3 different classes, okay? Match each distribution to the appropriate mean and standard deviation in the table provided. So let's look at this curve first here. I'm going to color it green so that we know what we're talking about. So this green curve, this is a normal model, and we know that its center of the model is going to be over its mean. So this green one looks like it has normal. It's normal with mean 70. And next we want to figure out its standard deviation. Well, it looks like almost all of the data is going to be between the mean and 85. So if we look at that, that looks like the standard deviation's probably about, probably about 5 for this model. So if we take that, using the empirical rule again, 85 minus 70 divided by 3. Okay, so the green normal curve looks like it has a mean of 70 and a standard deviation of 5. And so that corresponds with class A. So we can label that one A. All right, next, let's look at this other one, which is also centered at 70. We can see, but it has a much larger standard deviation. And we can tell because this normal curve is shorter and spread out much further. And in fact, it looks like 3 standard deviations from the mean bring you to 100. So this curve looks like it's centered at 70 and probably has a standard deviation of 10. And that would match down here with B, class B. So this curve is class B. And the next one we can look at is the dotted one over here. It is centered at 50, so we know it's normal with a center of 50 or mean of 50. And again, it has quite a large spread. It looks like 3 standard deviations. Most of the data would be between 50 and 80, again giving us a standard deviation of 10. That would be 3 standard deviations. So that corresponds with C. But so you can see that these 3 curves all have the same general shape, the bell shape, symmetric, unimodal. And the difference comes in where it's centered, and that's the mean, and how spread out it is, which is described by the standard deviation. So let's take a closer look at the normal model 62.5, 2.4. So this is going to be based on the mother's height data. So they had a mean. This is the mean was 62.5 and the standard deviation was 2.4. Okay, so just knowing those 2 pieces of information, we can get a model, a normal model drawn for us using StatCrunch. So the mean is 62.5, that's the center. And then we can see 1 standard deviation, 2 standard deviations, 3 standard deviations, and going the other way, 1 standard deviation below the mean, 2 standard deviations below the mean, 3 standard deviations below the mean. Notice that the tails of the distribution do not actually touch the axes, leaving open the possibility that a woman's height could be more than 3 standard deviations away from the mean, but it becomes more and more unlikely the further you get from the mean. The numerical scale on the vertical axis is not included and it's not needed for any of our calculations, so we don't really worry about that. How well does this normal model for the distribution of mother's height fit the actual data? So up here, this smooth curve, okay, up here is the normal model. That's how we're modeling our data. And down below, we have a table talking about our actual data. So if the model is a good fit for your data, then the area under the model should give us good predictions for the area under the histogram. So let's take a look and see how good this fit is. Shade in the area in the model that represents the probability of randomly selecting a woman between 55 and 60 inches tall. So up here on our model, 60 inches, probably around here, and 55 out here. So we're talking about this area. Okay. Estimate the percent of the total area of our shaded region. So one thing we can keep in mind is that this is a symmetric distribution, and right at the mean, 50%, I didn't draw a straight line, 50% is going to be less than the mean, and 50% is going to be greater than the mean when we're talking about a normal model. So that can kind of help guide us when we're trying to estimate the area of our red shaded region. So this looks like it's less than half of our distribution. I think it looks about 15% or so around there of our distribution that's shaded. So what is the actual probability that a randomly selected woman is between 55 and 60 inches tall? Now that's based on our data. If we look at our table, we can read it in our relative frequency table here that it's about 14%. And that's a pretty good fit. It's pretty close to our model. So our model is looking good so far. So using the model, we want to find the exact area under the model to find our probabilities. Finding area under a curve does require calculus, but we can actually use a table or StatCrunch to do this so that we don't have to do calculus. To find this area. And so we're going to look at the way we can actually find out this exact area that's shaded in. And so in StatCrunch, there's a way to do it. And I'll just show you very quickly how to pull that up in StatCrunch. So in StatCrunch, if you go to Stat, Calculators, to Normal, a normal calculator pops up for you and you can enter your mean and standard deviation that you're interested in. So I have one here for our women's height data. So I entered the mean of 62.5, standard deviation 2.4. And then I said that I was interested in this area between 55 and 60. And StatCrunch shaded in the actual area that I was looking at and gave me the area under the curve, which is 0.147. So that is where these diagrams came from. They were calculated in StatCrunch. And so we can compare what the model found to the actual. So our model found that the area under the curve was 14.7%, and the actual, which I'll write up here, was 14.1% that I'm getting from our table. So that's a pretty close, that model's fitting pretty good there. If we're looking between 60 and 65, the probability of finding a woman whose height between 60 and 65, the model says it'd be 70.2%. And our actual from the table says 71.6%. Again, that's a pretty close probability. So far, our model is looking pretty good. To look at a probability between finding a woman that's between 65 and 70 inches, our model says 14.79%, and our actual from the table was 14.2%. And the probability of finding someone between 70 and 75 inches is pretty small. It's 0.08% from the model, and actual said 0.15%. So I would say our model is fairly accurate for our data. So recall the empirical rule, which states that if one distribution is unimodal and symmetric, then approximately 68% of the data should fall within one standard deviation of the mean. 95% should fall within 2 standard deviations, and virtually all the data would fall within 3 standard deviations. Let's see if this holds true for our normal model for the distribution of women's heights. Okay, so looking at over here, the histogram is our actual data. And if we look at one standard deviation on either side of the mean, so you can see the shaded area is one standard deviation below and one standard deviation above, 68.2% of our actual data falls within one standard deviation of the mean. And according to the model, the normal model, 68.3% falls within. So this is a really good following the empirical rule. Let's look at two standard deviations. So looking at our actual data over here, 95.9% of the actual data fell within 2 standard deviations of the mean. And again, using our normal model, it says, okay, 95.4% fall within 2 standard deviations. So again, we're holding true. And the final one is that 99.8% of our actual data fell within 3 standard deviations of the mean. So this is one way we can see if the normal model is a good fit for our data by checking to see how the empirical rule works. So after we've taken a minute to draw our data in a histogram and find out whether it's unimodal and symmetric, we can see if the empirical rule holds, and then we can be pretty confident that the normal model is a good fit for our data. It turns out that we don't need to refer to the values in our distribution in the units in which they are measured. In other words, we don't have to be working in inches and talking about 62.5 inches when we're working with our normal model. Instead, we can use what we've already learned about standardizing our data, and we can use standard units instead. And this helps us find probabilities. So in other words, the probability that a randomly selected woman is between 60.1 inches and 64.9 inches is the same that a randomly selected woman is within 1 standard deviation of the mean. So if we looked at their mean and subtract 1 standard deviation, we get 60.1. And if we looked at their mean and added 1 standard deviation, we'd get 64.9. And so that's what we're looking at. We're just looking at what's going on between -1 and 1 standard units from the mean. So this is helpful because we can use a table to find our probability under the curve after we've standardized our data into standard units. So this model has a special name, and it is called the standard normal model, or standard normal distribution, and it has a mean of 0 and a standard deviation of 1. So these are our z-scores, and we have calculated them before. So z is equal to our value minus our mean over standard deviation. And so we can standardize our data and then use the standard normal model. Being able to use the standard normal distribution is helpful because it allows us to find the probabilities for any normal distribution without using calculus, but rather using the standard normal distribution and a standard normal table. So this special table is available in your textbook. It's also included in your note packet on the last page so that you can use it to look up probabilities right now. So it says below is a copy of a portion of the table, and the numbers in the table represent the areas or probabilities. So when I say in the table, we're talking about in here. These numbers are probabilities, and they correspond to z-scores. So what's the probability that a woman is less than 1 standard deviation above the mean? Okay, so up here, let's take a look at what we're talking about. So if we were asked the question, what's the probability that we find a woman that's less than 64.9 inches? We could standardize that to find out that that's 1 standard deviation. And so here on my standard normal, I might draw it in and say, okay, what's the area under here? What's the probability of finding a woman that's less than 1 standard deviation above the mean? So this whole area that's in red. How do we do this using our table? So along our table on the outside are z-scores. And as I said, this is just a portion of the table to look. So we're looking for a z-score that's equal to 1.00. So you start by going down this column until you find the z-score you're looking for, 1.0. That's in the down part. And we find that here. And then you can go across the top column here to find the 100th spot to match your z-score. So for us, that's 0, 0. So reading down here and across here, we get to this 0.8413. So it's 84.13% the probability of finding or of selecting a woman that's less than 64.9 inches. So let's write this out mathematically. Let's see, the probability of selecting a woman that's less than 64.9 inches is the same thing as saying the probability of getting a woman with a z-score that's less than 1, because when you standardize to 64.9, you find out that that's 1 standard deviation above the mean. And now reading that off the table, we find that's 0.8413. So let's use the standard normal distribution and the table to verify the probabilities from StatCrunch and get a little bit more practice finding the area. So here in our first example, we're looking for the probability of selecting a woman that's less than 60 inches, okay? So if we want to use a table to find out what's the probability of selecting a woman that's less than 60 inches, we need to first standardize that. Okay, so we're our value that we're interested in is 60 inches minus our mean over our standard deviation. And this comes out to be negative 1.04. Okay, so always we want to sketch in the area that we're interested in. We want to find the probability that we're less than negative 1.04. And we're going to use a table, which I said is included in your packet. So to find this probability. So we go down the Z column until we find negative 1.0. So here we are. It's going to be in this row. And then hopefully we can fit it both on here. Yep. So we need to come over to 400ths because we are interested in the number negative 1.04. So we get the negative 1.0 from the column and this 4 from the row. I'm sorry, from reading across this row up here. So this goes like this. This is the row, negative 1.0, and then we're interested, oops, see, that's why I did the long line. I went over too far. 0.1492. So going back over here, we find out that the probability is 14.92%. And that matches pretty closely with what StatCrunch found. Okay, how would we do it when we're looking for something between? Now we want to know what's the probability of selecting a woman that's between 60 and 65 inches. So we've already standardized 60, and we know that that's negative 1.04. So now let's also standardize 65. So that'd be 65 minus the mean, 62.5 over the standard deviation. And that comes out to be 1.04. So the area that we're interested in is this blue area. The table always gives us the area to the left of the line. So we have a little bit extra calculation this time. So our interest is the probability that we have a Z between negative 1.04 and 1.04. Okay, so when we look up 1.04, the probability of being less than, Z is less than 1.04, that is the table is going to give me this probability, the area, all the way from the red line over. So let's look up and see what that gives us. Going to our table, we want to go to 1.04. So just to make sure I'm all lined up, it's 0.8508. So the red is 0.8508. Okay, so that's this whole area. If we look up the probability of Z being less than negative 1.04, that's going to be this area, the green. And we found that already in the above example. That was equal to 0.1492. So how can we find the blue area? So if we take the 0.8508 and subtract off the green area, 0.1492, what we're left with is the blue area, which is 0.7016. So 70.616%, which is very close to what was calculated using StatCrunch. And then the final example I have here is to show how do we find out when we're looking for greater than, because our table is always set up in less than. So what's the probability of picking a woman that's greater than 65 inches? So again, you need to standardize that. So Z is going to be equal to 65 minus 62.4 over the 2.4, which equals 1.04 as we found. So the probability that Z, what we're interested in, is greater than 1.04. What does that look like on our graph? It's going to be this area here. So we always want to draw a picture and shade in what we're looking for. So when I use the table to look up 1.04, I'm going to get the area to the left of the line. And so what we do know is that the total area under the curve is 1. And so one way to find this is to say, okay, well, if I know the green part, I can do 1 minus the green part, which is 0.8508, and that will give me the blue part, which is 0.1492. So that is one way to find the greater than. So many times we are looking up to find out what's the probability of seeing some value. But there are other times when we're going to start with the probability and want to figure out what number would correspond with that probability. In other words, there are times when we're given an area and we need to find the value. So for example, how short would a woman have to be among the shortest 1% of all women? This type of number is called a percentile. So we want to know what is the number that corresponds to the first percentile. How will we do this? Always start with a sketch of your standard normal. So the information we're given is actually the area. So we're looking for what line here would correspond to a shaded region of 0.01. So we are actually going to use our table in reverse this time to figure out what z-score corresponds to an area of 0.01. So we are actually looking inside this part of the table, in the probabilities for 0.01. So 0.01 is down here. It's really close to one of these two things. So you pick the one that it's the closest to. So let's go with 0.0099. And that corresponds, reading the table backwards, to a z-value of negative 2.33. So we're going to be solving for a value. So remember that our formula is z is equal to x minus the mean, which is 62.5 over 2.4. We just looked up our z value on the table, and it was negative 2.33. So what our goal is to find out what height, our x, corresponds to this first percentile. And so we're going to have to do a little algebra. We can multiply both sides by 2.4. And then add 62.5 to both sides, leaving us with x is equal to 56.908 inches. So the first percentile corresponds to 56.908 inches. So one last piece of information before we wrap up this section. The first histogram below contains the heights from a large sample of adult women in the U.S. drawn at random from the National Health and Nutrition Examination Survey. The second histogram contains the weights for the same sample of women. A normal model has been superimposed over each histogram. Okay, so you can see the normal model in red. And which one is the normal model a good fit for? And so clearly this histogram is pretty much perfectly modeled by the normal model, whereas this histogram, which seems to be a bit skewed to the right, is not a good fit for the normal model. So that's why the first step is always to just look at your data and see, is a normal model a reasonable model to use? And if it is, then you're able to standardize your information and use the standard normal table to figure out probabilities. So figuring out whether the normal model is a good fit, the first step, looking at it, also using the empirical rule to determine whether it is a good fit. We're going to explore these ideas further in our lab 3. And so if we do not have access to the data, then we do need to decide if we think the data would most likely be unimodal and symmetric based maybe on some other information that we have. So it's a long section, but very important information.